So standard random graphs. I guess we didn't do that, but that's a thing to prove, right? So that generating function for a Poisson degree distribution is this little beast here. And that's a separate equation. Separate thing for you to do. Right. Okay, so most of the, again, if we just reach into this box, we've got a large enough N and M, we're going to get a network that has a Poisson degree distribution. And the generating function for those creatures is there. So let's look at what happens in this case. So this is just what we found early on, right? So R sub k, right? Again, the probability that a random edge leads to a node with k other friends. This is how it's connected to the degree distribution's generating function. First derivative divided by the first derivative evaluated at 1. So we're just going to take the first derivative of this thing up here, right? It's e to the minus blob times 1 minus x. So it's really e to the, that's a constant there. So if we differentiate this thing, it's e to the x times the mean. So the mean is going to come down. That's all that's happening there. That's the top, evaluated x. And on the bottom, we have this thing. We're going to do the derivative. And then we're going to set on the bottom, we're going to set x prime equal to 1. And you can see what happens when you set x equal to 1 or x prime equal to 1. This is e to the 0, which is 1. Which makes sense. We go back here, right? So it's set x equal to 1 for the original generating function. Then we've got e to the 0, which is 1, which is the sum of the probabilities. Okay. So what has happened? These things are going to, it's not the best layout here, but these two are going to cancel each other. This is just 1 because of this evaluation, and then we end up with this. And this is, again, this is what you observe here, right, is this is the same generating function. We've kind of traversed this before, but the generating function is the same, which, right, that's a unique connection, right? So this is fp of x is fr of x, and that's the case for these Poisson beasts, is that, right, the p sub k and r sub k are the same. Right? It's a weird feature of those two things. If we're running along an edge, we hit a node, the number of other friends that that node has is the same as if we randomly chose a node and looked at its number of friends. All right, so and for Poisson things, your friends on average have one more friend than you. They're not too bad, but not great. So our original, those two equations that represent the two pictures, the two recursion pictures, are the right-hand sides are the same, right? Because we have an FP and an F rho, they're the same. Sorry. FP and FR are the same, so now we can say this, that the generating function for pi and the generating function for rho, so again, this is the pi sub n and r sub n, right? These are component sizes. They're the same because they both match, they both have the same form. I know, it's exciting. Anyway, this is why our dirty trick worked before, where we did a bad thing. We said the probability that a node is part of a giant component or not part of the giant component, that's what we did, is equal to the probability that it has k friends and each of its friends are not in the giant component. And we said those probabilities were the same. And it's true, it's basically almost always true. It's just that those networks are you never find them in the real world. I feel like I am saying words, which is true, but not words that stick. It's important, I'll say the words. All right, I'll keep saying words. Okay, so ultimately we end up with this, right? Pi n is equal to rho n, just as pk is equal to rk. So again, very important mathematically and so on, but these distributions don't really exist. Questions? Ada.
Okay, so if the giant component is actually infinite,
Mm-hmm.
what do you mean by fractional size?
Yeah, so fractional.
Are these actually generating functions, or are they secretly limits of generating functions?
They are, so So that's the problem, right? So the n here, of course, is an integer, but the fractional size. So there are two things going on. One is that the pi sub n, you're going to have pi 1, pi 2, pi 3, right? What's the probability that you're part of a finite component of that size? But the probabilities, if you add up all of those probabilities, that's the probability that you're part of a component of a finite size at all. So 1 minus that, so that's why you can do fractional size, because 1 minus that sum, that's S1. What is it? Yeah, that's right. 1 minus the sum of all these probabilities is going to be S1. So this is a fractional size. This is the, or you can interpret it as what's the probability that the node you chose is part of the giant component. What was that?
Okay.
So what happens with these calculations is all about finite components, because that's mechanically everything works, right? You can compose pieces, and as we get to the right, so we have this transition, right? So average degree, and this is usually average degree 1, just for, say, just standard ones. Then, but let's not worry about that. We'll say average degree, critical, whatever it is. So as we're going along here, we're actually, every component is finite, and so everyone's on the team. But as we go past here, then all of this only applies to, all of the, and we just ignore this, or we step away from it. There is a better way, and we'll cover it, which not so much that you want to give up, but where you actually really can go into this, which is nice. No more generating functions for that. Okay, so we did this. Maybe not everyone is happy, but we're here. Okay, and so we just have this one equation, and in fact we can say to ourselves that the pi and rho, they're all the same, so we could write a recursion relation like this. We have our expression for the p and r, we have their generating functions, so we in fact have this structure. So you could try to undo this, right? This is it's pi 1 times x, pi 2 x squared, you could put it all in there and try to unwrap this horrible mess. You've got an exponential, so it'll be doable, right? I mean, you just expand this as a series and pick things off. It'd be quite unpleasant. Anyway, so we could start with this, though. We're interested in, say, what's the size of what's the fractional size of the giant component? So we're going to set x equal to 1, and that will give us something we can work on. And in fact, matches up exactly with what we had before. When this was I guess we did it as delta, right? So this is delta, and it was e to the minus average degree 1 minus delta. So we get exactly the same result. But it's because we've been much more careful now, and we've noticed that the Poisson degree distribution networks have this property that we sort of asserted. Yeah. Much trickier. But the game is, you come back here and you say, right, this is x equals 1, and then we know that this sum of all of these probabilities is 1 minus the probability that we're in the giant component, which is the same, we can say it's the same as the fractional size of the giant component. So this blob gets replaced by 1 minus S1. 1 minus it will just get replaced by S1. So that's here, it just becomes S1. This becomes 1 minus S1. And so that's something we can play around with, and in fact we noticed that you could actually one could express the average degree as a function of the fractional size, so we could plot it, right? We don't have to solve it. We could plot it if we want, in a simple way. Lara. What is x again? So x is this variable, so what we're going to do is say f of p of x, right, is right, we're going to take our distribution, p of 0, p1, p2, and then just attach these things to it. So it's a variable. It can be anything, right? We're allowed to play around with it. And it's yes? Right, so it doesn't have that feel to it. We're off in crazy space, right? I mean, maybe this. So with Fourier transforms, for example, some transforms, very real, right? So that's a frequency or the wave number. This is a completely different game there. Here, this is a mathematical. We're going to think of it as a mathematical craziness, right? And the big thing for us is, if this is an x cubed and then we multiply by another one of these things that has an x4, then x cubed plus times x to the 4 gives you x to the 7. So it has a little mechanic, right? There's a little machinery that we've created, which would mean that the probability multiplying that x cubed and the probability multiplying the x to the 4 over here would multiply to each other. So that's just to give you some sense of how it helps you do calculate, right, so you can avoid, you could just multiply these two functions together knowing that, and they could be functions like this, you see, right? It could be just, the top one, see, right, it's just this function up here. Some blob. We could multiply two of these together, and instead of doing all of these little calculations one by one, and then so we can do that multiplication and then sort of undo the whole thing. And so it gives us shortcuts. It means you do a bazillion things at once. Yeah. Sort of? How do you feel about that? There are a couple of values of x that we will use constantly. One is 1. When we set x equal to 1, right, then we've got a sum of probabilities. So that comes up a fair amount. Setting x equal to 0, not always useful, but it's in the inversion formula we use it there to get rid of a whole bunch of them, right? Because if you set x equal to 0 here, you just get p of 0 because it's x to the 0. And if you differentiate a whole bunch of things and then set x equal to 0, you can peel off the p to the 23, p of 23. So that's when x equals 0 kind of popped up, but x equals 1 is more what we want. And that usually means you've done something, you've messed around with it in some way, and then you've summed things up. Right, so if we took a derivative of this, we get a k down here. And then we set x equal to 1, that's the average of k. So, yeah, so generating functions often, derivatives are good things, multiplying together, composing them. We do those sorts of things, which are a bit, we don't have we're not differentiating probabilities, right? They don't have that feature to them. We multiply probabilities together, add them together. But we can achieve that in some weird function space. When you go back to probability space, you set it to 1, or if you want the whole this distribution you've kind of created, right? So you find your generating function somehow, and then you want to undo it to find what the real probabilities are. Then what you're going to do is lay it all out so that there's something times x to the 0, something times x to the 1, something times x to the 2, and so they're just like little signs. So the x to the 3 is just holding up a sign that says the thing that's attached to it, that's multiplying it, is the probability of a 3. So they just become little holders. And because of math, these holders can do nice things with each other, right? When you multiply them together and stuff, yeah.
So they're just used to do stuff.
Yeah. I mean, I think that's fair. I mean, does that seem fair, or is there some beautiful interpretation of? Whereas in, say, Fourier and so on, it's quite different, right? There really is. I mean, again, there's all these sort of magical things you can do with them, but there's actually a deep interpretation of them. Here, it's completely fine to think of it as just sort of this, contraption.